You just don't want me to start. Okay, as you guys shovel food down your gullets. Hey, so what about Germany? Oh my goodness, huh? Uh-huh. Germany kicked Brazil behind. Okay. All right, here we go. That was my World Cup thing for the day. Okay. I don't watch it, but. Okay, you guys ready? Shh. Now, you shouldn't be talking if you're filling your face. I could be talking, filling your face at the same time. Okay. All right. So we're in our section on renal physiology, which for some people find it very difficult. He's like, what? Some people find it difficult, maybe not everybody, but it tends to be a little bit harder than most. But today's lecture should be piece o' cake. No pun intended. Oh, well, I remember, though, because I couldn't tell you when you took your lab exam. Thursday, I went to WinStar. Yes. About $200. Good job. No, I didn't play poker, though. All right. So we're going to do is to start it all off, talk about body fluids, body fluid compartments, a little review, and I mean review, of osmosis, because you should know what osmosis is, because that understanding osmosis is critical when you do renal physiology, especially when we get to the lecture about maintenance of water balance and the role of the kidneys and what's going on in different parts of the nephron tubule. Because if you don't know the principles of osmosis, you won't understand why fluid is moving from inside the nephron tubule out or the opposite way or not moving at all. Because it all depends on the different part of the nephron tubule. Is it permeable to water or is it not? Because then when you learn the definition of osmosis, what was the definition? The movement of water across a selectively permeable membrane from its high concentration to low, right? So you're assuming it's permeable to water, but not every part of the nephron tubule is permeable to water. But if it is, water will easily move across. So we'll look at that. So let's start with just the whole concept of fluid balance. And you don't memorize these values, but we're taking in fluid all the time. Some of you are. You always got a big thing of water right there. We drink, drink, drink. So you take fluid in your food, liquids. So fluids coming in, we're losing fluids all the time. You lose it, a little bit of fluid in the feces, some in urine, if you're sweating, when you breathe. There's a lot of different ways that we're losing fluid. We want to be in balance, right? It's all about homeostasis, correct? You don't want too much in, not getting it out, or you don't want to have too much out, not getting it in, because then we would not be in homeostasis. Because why is water so important in our bodies? It's a very large percentage of our body. Why is it so important? What do we use water for? Some say everything, but it's, yeah, pretty much true. It's a solvent. A lot of things are dissolved in water. Metabolic reactions take place in water. Water is going to be important in temperature regulation. Water is pretty important. So we're a big bucket of water. So we want to make sure we have adequate levels. Okay, so we're going to be looking at the role of, specifically later, the kidneys are going to be real important in it. But I do want to mention this term here, something called insensible water loss, meaning because you're usually not aware of it, you don't have sense of it. Or, to me, it's like, it makes no sense why we're losing this water, because the other way where we have sensible water loss, there's a reason. It makes sense. So let's just think about sensible water loss. Urine. Does it make sense we have to lose fluid in urine? Because you have to have those waste products dissolved in fluid. So it makes sense I need to have some fluid lost in urine. You got to have some in feces. I'm sorry, a little bit in the feces. Makes sense if you're sweating. involved in temperature regulation. But there's a couple ways that we lose water all the time. To me, does not make any sense. And then usually most people are unaware of it. Right now, you're losing water through your skin. And I'm not sweating right now, but I'm losing water. So even though we have a very good, you're going to tell me, what is in the skin that allows, it kind of acts like make it water resistant. It limits the amount of fluid that we lose. Keratin, okay? So we do have keratin, and that limits how much water that we're going to lose, but we're still going to lose some. So getting it through the skin, and it's not sweating. So this is independent from sweating. And when you breathe, every time you exhale, you're losing water. Because when you exhale, it's carbon dioxide and water that's coming out. So that's insensible. You don't really have control over it. So if I want to maintain water balance, what's the best way to control it? There's certain ways I'm like, I'm sorry, I have to lose this water for certain things. Can't really sweating. You want to sweat for temperature regulation. So I'm like, I'm not going to, if I need to conserve water, I'm not going to stop sweating. So what's the best way? Urine output. So the kidneys are going to play a real important role. Let's mess with the urine output. I could get it down to a minimum level. I still need some water that I have to get rid of some waste products. But your urine output can be as little as like a half a liter a day. It's 500 mils. So anybody have a liter? Well, mils is that? It's about just a little bit bigger than this can. Would be like the minimum. But you can actually have urine output up to like 2 liters a day for those of you just down in the water and down the water and down the water. You can get rid of it. So that can fluctuate. So kidneys are going to be the biggest way that we can control water. Because sometimes you don't have always access to that fluid. Everybody's still drinking away. Are you getting thirsty just by talking about this? Was it water or something else? Okay. So how is insensible water loss minimized? We said it's pretty much having that nice intact integument. Does everybody realize that your skin is the largest organ of your body? Someone said, skin's not an organ. I'm like, yes, it is. It's the largest internal organ in your body, though, is what? The liver. Okay, but skin is the largest organ. So intact integument with nice keratin helps to minimize it. But if you're a burn victim, you got a lot of problems. When you're a burn victim, and actually there was that guy that just lit himself on fire, I think it was yesterday. He lit his T-shirt or whatever, wife beater up on fire and just walked through. No, I think it was like someone said, you know what I mean, well, wife beater. What do they call them? Wife beater. Everybody know exactly when I say it's a wife beater. Okay, the white T-shirt tank thing. Okay. He lit himself on fire, and a few, I think it was police officers, or were they firefighters? I think it was police officers, that, because he was walking through some like public building or something, and they brought him down. I think she's the police officer. Was burned over 15% of her body. She's in the burn center, I think at Parkland. So what's so dangerous about having significant burns? There's a lot of things. What? Why are they? Okay, what were you guys talking about? Something. Oh, was that path? Okay. Are you going to tell me? Oh, you guys had an exam today, didn't you? You're like stem cell, didn't you? Well, yeah, because at the sternum basal, those are actively mitotic. You lose them. Sorry, it goes below that. You don't have any skin. Okay, but if it's before that, third. Okay, I get it now. Took me a while. I was like, what are you guys talking about? Okay. But what's the other thing? Why do they have, they're in special places in the hospital. They're in burn units. They have higher risk for infection. They're going to have issues with dehydration because guess what? They're not minimizing that insensible water loss. So they're going to be on IV fluids. So they're going to have infection's going to be a problem. Temperature regulation will be a problem. So, but yeah, so got to be careful with that skin. But there's some So let's kind of look at, don't memorize these values, just kind of think logically. If I say intake should equal output, you're exercising real intensely. Tell me what should, for fluids ingested, will that change? Maybe, maybe not. I'm exercising. What if I didn't bring my water bottle? Could that be a question mark? Intake, but if I don't have enough fluid intake, what do I need to be able to try to maintain homeostasis? Other things may have to change. So I'm going to say, let's put a big question mark by fluids ingested. But look at these other things. I filled them in for you. Insensible water loss through the skin. Not going to change. Because remember, that's independent from sweating, right? That's not going to change unless all of a sudden you're intensely exercising, you fell down and scraped your body up. But we're assuming that you didn't do that. Lungs, though, it's increased. Why would insensible water loss through the lungs increase during heavy exercise? Because you're breathing more. So you're going to lose more just by breathing. Definitely going to sweat, I would hope. Feces, I shouldn't change. I'm assuming you're not pooping while you're running and stuff, okay? Hopefully. Urine, though, would hopefully decrease. So hopefully, though, the amount of water that we're losing by sweating and from breathing, and if I'm kind of question mark by my intake, I can maintain homeostasis. But we know there's an issue if we don't. You can get dehydrated, right? Don't people get dehydrated when they're exercising? Especially out in the heat. And it's going to hit over 100 this weekend, just to let you know. It's supposed to hit over 100. So be careful about exercising outside, okay? Well, considering just, since it's here, this insensible water loss through the lungs for exercise, could that also be an issue up in Denver? And I'm not exercising in Denver, I'm just hanging out in Denver. Why would insensible water loss increase while I'm in Denver? Higher altitude, one of the responses of being at the higher altitude, because of the low oxygen, I start to increase my respiration. So I mentioned last trimester that they have those signs out in Denver and those places people are going on hikes that you can dehydrate. So make sure you bring plenty of fluids because you're going to be breathing more. I mean, you say, well, you're hiking. No, but they're going to be breathing more just because the oxygen is, the partial pressure of oxygen is so low up there. So why, you already answered this one. Why is the loss through sweat increase? Because what's the purpose of the sweating? Temperature regulation. We even have a lecture this try about temperature regulation, so sweating will come into play. And why is the loss of the urine decreased? That's done on purpose. That's just to allow you to maintain homeostasis. Yes?
There's going to be a contribution. You've got 200 coming from metabolism.
Mm-hmm.
Shouldn't there be an output going towards the normal functions of the cells in the body?
What do you say? Oh.
Like, you have an intake from metabolism, so you're getting it from the cells breaking them down. Shouldn't there be something from the output going into those cells? Or is that just something you do after that?
Output going in the cells.
If you're getting something from cell metabolism,
Mm-hmm.
should there be something
That'd be from like the electron transport chain.
Should there be something going into it from the output? Should that be equal?
I don't know. You just normally make some water just because of electron transport chain. I don't know.
Those cells take in water?
Well, yeah. As long as it, but water will only move if there's a gradient. It's always going to maintain osmotic equilibrium.
Because if you have something coming out of it, wouldn't there be something in it?
Not necessarily. Not necessarily. So maybe if we review the principles of osmosis, we can maybe figure that out. So remember, water will only go from its high concentration to low, again, as long as the membrane is permeable to it too. Okay? All right, so let's talk about water that we normally have. Extracellular fluid, intercellular fluid, and you were talking about out and in. So most here's this, remember this number, 60, 40, 20. 60, 40, 20 rule. Your body weight. 60% of your body weight is water, on average. You have some people a little more, a little less. 60%. So if you want to lose weight, you don't go and dehydrate yourself. That's not the smart way to do it. Okay, so no, it's like, well, I got to get rid of some water, and then I'm going to be skinnier. No, you're just going to you're going to mess yourself up. Okay. Huh? Yeah, but I know they put those sweatsuits on, make weight. That's what the wrestlers do. They do that. My nephew's a wrestler, and his dad will do whatever he can to have him make weight. I mean, he's keeping him watching what he eats, but they go in, get weighed, and oh, you got a few hours, you got to make weight. They give you a little leeway. So guess what he makes him do? One of the things he makes him do is gives him some gum, starts to chew, and he spits it out. Chew, spit, chew, and he's made weight doing that. They do that. Wrestlers do that, and it's just water weight. It's just enough to get on that scale. Oh, you make your weight, and then he goes and eats whatever he can. As soon as he makes weight, he goes and eats, and then he waits the next tournament, and then he starves himself. Wrestlers are worse than a lot of other people because they starve themselves just to make weight. Okay, so as I digress, but it still had to do with water. About 60% of your body weight is water. All of that water, most of it is found inside your cells, in the intercellular fluid. So 40% of your body weight is water inside your cells. Okay? The remaining is in the extracellular fluid. Okay? That's your 20%. So 20% of your body weight is water found in the extracellular fluid. What's part of your extracellular fluid? Well, that would be your plasma. That would be things like synovial fluid, cerebral spinal fluid. Those are all examples of extracellular fluid. Okay, so that's your 60, 40, 20 rule. Okay? Most of that water is inside the cells. One of the things we're going to be shortly talking about, though, is that distribution of water may change if something happens. If something changes the osmolarity, water is going to move so it maintains osmotic equilibrium. Always remember, water only moves passively. So it's only passive movement, but it's following where all the solutes are. So it wants to make sure the osmolarity inside the cell and outside the cell is the same. So right now, we're all normal. Everything's good. So we got a normal amount of water inside, normal water outside the cell. Okay? So, other thing, though, I want to remind you about, a little review before we move on, is we're going to talk about some anions and cations, but let's just do a double check. Let's do some math. Okay, no one grumbled. That's good. Brain, yeah. I know, yeah, that's true. You ate cake, falling asleep. Okay, all right. There's a 150-pound man. That's a light man, okay? 150-pound man. What's the weight due to water? How would you set it up? Just set it up. 150 times 0.6 was about 90. Did I do it? You guys have your cell phones. 90 pounds of that guy is just plain old water. Okay? You may have to do this on your lab exam, too. Okay, just let you know. All right. Now, if this person's... Well, no, I mean, if I say it in pounds, I can do it in pounds. I'd have to change this to kilograms. But I'd say if I gave it his weight in pounds, I'd have to give it to him in kilograms. But I gave it to his weight in pounds. I could give me the calculator and I'll figure it out in kilograms, but I'm not doing that. Okay? Because you'd have to convert this to kilograms. All right, if the TBW, that's total body water, TBW. If his total body water is 40 liters, this is a completely different story. 40 liters. And I say their extracellular fluid volume was 15 liters. How much fluid is inside the cells? I'm all water, got a whole bunch of water. That water is inside and outside the cells. I'm giving you what's outside the cells, what has to be in the inside. This one's not a bad one. 40 minus 15, it's like, Yeah, it wasn't that bad. 40 minus 15, so how much water is in the intercellular fluid? 25. That one math's not that bad. Do I have to do a math to how to do subtraction? Okay. It's usually division's the problem for most people instead of addition and subtraction. I'm just a little quick check of your math skills. Huh?
But if you have to change the weight to kilograms, then it won't be 90.
Oh, no, it won't be 90. No.
Then that you have to change it to kilograms, right?
No, I don't. I didn't. It's 150 pounds, 90 pounds.
Okay.
But if I gave it to you in kilograms, yeah, you can do it in kilograms.
We did some samples.
You did, I think, everything in kilograms. Yeah, you did everything. I just did in pounds. Because most of you guys hate kilograms. I just did pounds. Okay. But in lab, you did kilograms. All right. So, as a reminder about the electrolytes, this is going to be important very soon. You should know which electrolytes are found in heavier concentration outside or inside the cells. There's two of them that are very important for me right now that you remember. Sodium and potassium. Those are the two very important ones. Sodium is heavily concentrated in the extracellular fluid. That's really important, okay? Potassium, higher concentration inside. And kind of having that different distribution was involved in your resting membrane potential. It's going to be important when you talk about action potentials, all that good stuff, okay? Who remembers the mnemonic for keep your sod, sodium, outside to grow your, no. Remember, the pot's not outside, not here. So you grow you have your sod outside to grow your clover, because chloride is heavily concentrated outside the chloride, okay? Grow your grow your clover. You keep your pot inside, and the clean one is you keep your pot inside to cook your bacon and the eggs, because bacon and eggs are proteins and negatively charged. That helps you remember about why resting memory potentials, you got a lot of negative charge inside the cell. So it's to cook the bacon and the eggs, or you keep your pot inside if you don't want to get arrested, okay? You grow it inside the house with all the little lights and stuff. We're not in Oklahoma where it's, no. I know Oklahoma has a lot of pot farms because it's rural. They can't find it. It's rural. I mean, there's acres and acres of stuff, and it's easier to hide it in Oklahoma. And I've had a lot of people from Oklahoma that admits to it. So not that they themselves grew it, but yeah. But they do it, just as long as you don't grow it in your backyard. Don't grow it in your backyard, okay? But that's the way to remember it, okay? Actually, when I was in college, I went to visit a friend, and I think they were in Rome, New York, and we went over. I think it was his brother's house. They had in the room. They opened the room. It was like there was a lot of plants growing with a little light, artificial light in there. They're growing some pot in there. It was not legal. It wasn't for medicinal purposes either. All right. I know, that was a long time ago. I didn't partake, okay? All right. Disappointed at that time. I'm not perfect. I've made mistakes, okay? All right. Blood volume, kind of like a little subset, talking about extracellular fluid, intercellular fluid, just like the blood itself. The blood cells, the fluid inside the blood cells, Juliana, right behind you. That would be intercellular fluid. The plasma is an example of extracellular fluid. Would we agree? Okay, it is. Okay. Your blood volume happens to be about 5 liters. And the way to remember that, how did I tell you? I actually told you about this a long time ago. How do you remember that? Your blood volume is about 5 liters. 5 liters. What's our cardiac output? About 5 liters per minute. So we move our blood volume within a minute. That's the way you remember. It's about 5 liters. your hematocrit. What's your hematocrit? If I measure your hematocrit. So if I take a sample of your blood, spin it down a little centrifuge, these kind of things separate out. You got your blood cells. Here's a little called a little buffy coat. Those are your white blood cells. And then you have your plasma right here. So your hematocrit has to do with the percentage of formed elements in that blood. And since most of your formed elements are red blood cells, sometimes they'll say it's a percentage of red blood cells in it. Well, say this is a normal hematocrit. Girls, we have a little less than guys because, you know, we lose blood every once in a while, okay? This person has a higher, lower hematocrit. Higher. This person has a lower because of what? This one has more red blood cells. This person doesn't. But let's mention another way our hematocrit can change, and that having to do with the number of blood cells. So I spin down your thing, and I'm going to try to get right next to this guy. Spin it down. Same amount of blood cells, but I have less fluid. What has happened to my hematocrit? Because remember, hematocrit is the percentage of formed elements in it. So my hematocrit has done what? Increased because I've lost some fluid. Could I have an increased hematocrit because, again, same amount of cells, but I have more extracellular fluid, more plasma? Yeah, that's going to be important a little bit later. Okay, so you can have changes in hematocrit because the number of cells have changed or the volume has changed. Because remember, it's a percentage. Think of it as like a concentration. The number of these formed elements in this amount of fluid. Okay, so just put it that way. Okay? So let's get into the tricky stuff. And then we'll get into some stuff that's going to make your head spin. It's going to be good. Makes you think. Let's do a little review, Physio 1 review. Physio 1 flashback. Woo, okay. Ready? Again, you guys are dead. Wake up. Okay. So movement of water inside and outside of capillaries, inside, outside the cells. Remember the balance of hydrostatic forces and osmotic forces, talking about the Starling's forces. Do you remember that? The plasma colloidal osmotic pressure and hydrostatic. Kind of remember it a little bit? Okay. All right. So depending on the balance of those forces determines where the fluid is going to move. So if you mess with hydrostatic pressures or osmotic pressures, you can affect the movement of fluid. So now we're really only going to talk about osmotic forces, principles of osmosis. Remember, though, that when we talked about the plasma colloidal osmotic pressure and the osmotic pressure here, I said it's mainly due to the presence of what that created the osmotic pressure? Proteins, okay? But you need to remember, though, if you start messing with the levels of electrolytes, that can affect the osmotic pressures too. The sodium levels in your blood plays a very important role in osmotic pressure. And actually, if they measure your sodium levels in the blood, which they can calculate your total body osmolality based on that. So that's a very important factor in there. So if you mess with sodium levels, guess what? You're going to affect osmolarity, and you're going to affect how movement of fluid across different cells, across membranes. And that's what some of the things that we're going to talk about today. Okay? So, but let's review a little bit about principles of osmosis. I'm going to show you a real cool trick thing that you can do at home if you want. So first, remember principles of osmosis. You already told me what the definition is. You got a selectively permeable membrane. So in this case, this thing does not let proteins get through, but water can move across. So if you've got a lot of proteins over here, then over here, where does water want to go? It wants to go where all the proteins are because water was more concentrated here. So it's going to go down its concentration gradient. But remember, it always follows the solutes to a point where then you have a balance with osmolarity on both sides of the membrane. So water will always try to move into a point you maintain osmotic equilibrium. That's assuming that membrane is permeable to water, okay? So here it's moved until the concentration is the same, but we have a difference in actual amount of fluid, right? But the concentration is going to be the same on both sides of the membrane. There is a difference. You'll hear me using the term osmolality and osmolarity kind of interchangeably. But before we do that, let's review what an osmol is. So do you remember 6.02 times 10 to the 23rd? Remember learning about that? Avogadro's number. Oh my God. You remember something from high school. Okay, because it was from high school you learned it. Avogadro's number. 1 mole, osmol, is 1 mole of osmotically active particles. That means it allows, water's going to be drawn to you. It's got to be osmotically active. If I have a mole of glucose and a mole of sodium chloride, there's a difference. Glucose, if I have that in a liter of water, we call it 1 osmoles per liter. But sodium chloride, it's 2. Why? Because sodium chloride, if you throw it into water, what happens? Got the sodium and you got the chloride, and both of those will be osmotically active. And so the osmolarity is actually going to be higher than you have with a mole of glucose in water. Now, we're always going to do everything in milliosmoles. And instead of osmoles, it's going to be milliosmoles. Who knows the difference between osmolality and osmolarity? And they could be potentially the same. What's the difference? Anybody know the difference? The spelling, yeah. The spelling, yes, the spelling is different. Osmolality, if you have a mole of a substance in a kilogram of water, osmolarity is a mole of the substance in a liter of water. And I said they potentially could be the same because pure water, 1 liter of pure water is a kilogram. So if it's pure water, it's going to be the same. So there's just a slight difference. I'll sometimes go back and forth, osmolality, osmolarity. You'll still get the idea. So it's just like if I have 5 osmoles over here, 2 osmoles over here, where's water going to want to go? If it's 5 milliosmoles per liter here, 2 over here, where does water want to go? From the 2 to the 5, and to the point where then it's going to be balanced. And so our end result, it's going to be somewhere between 2 and 5. But they're going to be the same on both sides. Okay? Just the principles still apply. Don't worry about the difference between osmolality and osmolarity. This is a number that you will see very shortly, not today, but later. Just kind of keep that in mind. So body fluids is about 300. In reality, a little bit less than that, but it's about 300 milliosmoles per liter. So I say general osmolarity of your blood is about that value, approximately. Okay, so just kind of keep that in your mind for a later date. So let's watch. Shall I come back here? Let's watch a little. I'm going to fast forward through part of it because it's way too long. This concept of hypertonic, hypotonic. I know you went over that before. When we talk about hypertonic and hypotonic solutions, do you remember going over that before? So they use that term when they're talking about what's the effects on the cell. So if I put a cell into a hypotonic solution, what does that mean? The solution is what relative to the cell? Less solutes, okay? If I put it in a hypertonic solution, that means the solution has a higher concentration than the actual cell, okay? But doesn't it affect the cell volume, though, if you put it either in a hyper or hypotonic solution? So if I put a cell into a hypotonic solution, you told me out here the concentration is less than inside the cell. Where does water want to go then? Inside the cell. And it's going to change your cell volume. If you place me into a hypertonic solution, water is going to leave the cell and the cell will shrink. What you want to do is place the cell into an isotonic solution so you don't have any net change in the cell volume, which can affect the function of the cell. So if I have to go to the hospital, I'm a little dehydrated, and they want to replenish some fluids, and I'm sorry, I'm kind of out of it, I can't drink anything. They're going to put an IV in me. they need to want to make sure they put an isotonic solution in you, right? Because otherwise they're going to mess with you, make things worse. So that's where the 0.9% saline comes into play. 0.9% saline is same tonicity as you have for your body fluids, okay? They give you 2%, bad. They give you distilled water, that's worse. Okay, both of them are bad, okay? So I'm going to show you in visual form. This is kind of cool. This is something you can try at home. Take an egg, okay? What these people did, and I'm going to fast forward to it, though. They took an egg, and they put it into this solution to slowly dissolve the shell of the egg. Because if you actually look at an egg, and just eat a hard-boiled egg, peel it, there's a little membrane from the shell right over the thing. It's a membrane. So this membrane is going to be a selectively permeable membrane. So they're going to remove the shell, and they're going to keep this little membrane on it, and they're going to place the egg into different solutions and then watch to see what happens to the egg if you place it into a hypertonic or a hypotonic solution. The first time they did it, one of them didn't work as well. There's like, oh, this doesn't look like it's significantly different. But let's just switch it out. Let's put it in here and see what happens, and you're going to see what happens. It's kind of cool. So this is something you could always do at home because I think it's kind of a cool idea. Because all they did, I think the hypertonic solution they put in was just corn syrup. That's what they stuck the egg is in corn syrup. So you can always try these at home, okay, if you want to do it. Especially if you've got kids. Something to show for the kids. So let's... I already moved this. I have it open in another one. Oh, come on. There we go. Okay, should play. Stop it. There you go. It's under buffer. As it buffers through, this internet's been... Oh my goodness, really? Come on. Oh my gosh, really? Why is it taking so long? Because I'm asking for it? It's like watching water boil. And Firefox should be the better browser. Well, let's try it using different. Ask me later. Watch the other one will start. It might be just the internet. Okay, there we go. Skipping 3-2-1. Actually, I'm going to close this one out so it doesn't accidentally.
For example, water is considered a hypotonic solution since it is very low in solutes. A hypertonic solution is a solution that has a higher concentration of solutes compared to the cell's inside environment. For example, water with a lot of salts is considered a hypertonic solution since it is very high in solutes. How can we examine the effects of a hypertonic solution on a cell? You might be thinking, well, I'm made out of 50 to 70 trillion cells. If I drink this, I'll know what happens to cells in a hypertonic solution. But do not do that. Drinking salt water can be very dangerous as it severely dehydrates you. Nausea, vomiting, and even hallucinations are just a few symptoms of drinking massive amounts of salt water. Ask anyone who's been stranded at sea, which is unlikely because people who drink seawater eventually died due to kidney failure. So what you really need is a lab animal to conduct your test. Darn, she's too smart. Time to try her older brother.
They just did water and milk. They would not. That would have been bad. They put milk. They just make. They're not really drinking salt. They just put water in milk. Yeah.
Well, that was a bad experiment. What's a better way to test how a cell reacts when placed in a hypertonic solution?
It's like, oh. Okay. Okay, so they're going to do the egg cell thing. So I'm going to, here we go.
Shell in the way. Dissolve the outer shell by placing.
So they're going to dissolve it. There you go. The egg looks really cool.
Before starting our experiment, we will first mass our egg using a scale. Egg A has a mass of 94 grams. Egg B has a mass of 103 grams. Egg A we will place in a hypotonic solution, water. Egg B we'll place in a hypertonic solution, thick and sugary corn syrup.
Look at that one. That thing's, wow.
Egg A now has a mass of 97 grams. Egg A increased slightly to 103% of its original weight. We can conclude when a semi-permeable cell is in a hypotonic solution, water will enter the cell. Egg B now has a mass of 59 grams. Egg B decreased to 57% of its original weight. We can definitely conclude that when a cell is in a hypertonic solution, water will leave the cell. In fact, this is evident by the layer of water sitting on top of the corn syrup. However, 103% change in mass is not very significant. So how about we try this experiment again, but switch the eggs? This time, egg A is going in the hypertonic solution, which is still on the right. Egg B is going in the hypotonic solution, which is still on the left.
Shrinked up one. So now it's real obvious. That thing just swelled up. Isn't that cool? You want to do this at home? I think it's cool.
After several hours, mash your eggs again. Egg A went from 97 grams to 55 grams. Egg A has decreased to 57% of its original weight. Egg B went from 59 grams to a whopping 105 grams. Egg B has increased in weight to 177%. From this experiment, we can definitely conclude that when a cell is in a hypotonic solution, like water, water enters the cell. On the other hand, when a cell is in a hypertonic solution, like corn syrup, or more realistically, salt water, water will leave the cell. Now that you're done with this experiment, time to play with those shellless eggs. No, no!
I'm going to eat the egg now. Let's see, go back. All right, so something that we're going to do after you get back from your restroom break, got to remember something. If it's effective osmol, sodium, glucose are effective osmols. Generally membranes are not freely permeable to those things, right? We agree? So water's going to be drawn to it. If a membrane's freely permeable to you, you're not effective osmol because I can go back and forth, back and forth. Urea is something that's considered not to be an effective osmol because membranes are usually pretty permeable to urea. So that one's not. But things like sodium, glucose, they can be effective osmols. So examples, things that we're going to do is we're going to mess with sodium levels, though. When you get back from break, we'll mess those, and we'll figure out where water's going to move. Glucose could be an issue if you're diabetic. Because remember we talked about and I'm talking about diabetes mellitus, and I said, why do they pee a lot? Because when they're filtering their blood in the kidney, you get all this glucose, and you should be able to reabsorb in the nephron tubule, some of the things that we're going to talk about next week. If you have transporters, allow us to reabsorb all that glucose, but if you exceed your ability to reabsorb it, guess what? Glucose is an effective osmol. Water is going to be attracted to it. And so you're going to have a lot of urine output because of the effects of what glucose is doing. It's drawing, call it an osmotic diuresis. They get people that are diabetic, so they get that. So there's a difference between being ineffective or a not an effective osmol. So what we're going to do when you get back, we're going to be doing some little important concepts. I'm going to give you some clinical scenarios. I'll kind of lead you, push you a little bit. And I'm going to see, can you tell me what's going to happen? Is water going to move across the cell? Will the volumes change? Will the osmolarities change? So I'm going to make you do that when you get back. Now these terms, before we give you a little restroom break, isotonic, we said isotonic, hypotonic, hypertonic. If I use osmotic, I'm going to use them almost interchangeably though. But this is when we're doing the term tonic, we're talking about membranes that are selectively permeable to those particular substances. When you use the term osmotic, we're not necessarily assuming things are selectively permeable. But if I say this solution is isoosmotic, it means it has the same osmolarity. If it's hyperosmotic, it's higher osmolarity. If it's hypo, it's lower. Where those terms will come into play is when we start going through all the steps in the nephron tubule, and I say that fluid that's in the nephron tubule, is it iso, hyper, or hypoosmotic to your blood or to your regular body fluids? That's where those terms are going to come into play when we do those a little bit later, not today. Okay? So take a break. When you get back, we're going to go through some little scenarios. Okay? Yeah. It's effective. All right, who's got a practical today? Okay. I'm just asking. Making small talk. No. Because I was saying, it's like, depending on how I go through this next thing, you can be done early, or you may not. I guess I'll have to walk you through it instead of having you walk through it yourselves. But I'll try. I mean, I'm not completely do it for you, but I'm going to have someone help me. Okay? I'll have Robin help me. What? She's like, darn it. Dang it. No. I'll let them be willing participants. Okay? To help me walk me through these steps. Okay? So if I gave you these scenarios, if you had to work them out for yourselves, these are things I wanted you to realize, okay? But you may have to do a scenario on an exam, so just kind of remember that. Is water, as long as that membrane is permeable to water, water will always move fairly quickly to make sure the osmolarities are the same outside and in, okay? In the scenarios, we're going to say the cell membranes are pretty much not very permeable to solutes. Water, we'll say pretty permeable to water, but not to solutes. So, the number of osmoles, either in the inside or the outside of the cell, will only change if you add or remove them. Okay? So you're only add or remove them. So otherwise, they're going to stay constant. Okay? Remember when we talk about osmolarity, think of it as a concentration. Number of substance in a certain volume of water. It kind of uses the analogy of being a concentration. So if I keep the number of osmoles the same, but I change the volume it's in, that will change the osmolarity. Okay, so just remember that. Okay, so these would be the steps that you would take with the scenarios. You always start with what's going on in the extracellular fluid. We're going to do something to the extracellular fluid first. You start from there. If you do not have a change in osmolarity, water is going to stay where it's supposed to. But what you will do is you'll change the volume of it. If you haven't changed the osmolarity of the extracellular fluid, the only thing you'll be changing the volume. Added some, removed some, but if you didn't change the osmolarity, water's not going to move anywhere. But you mess with the osmolarity, water is always going to move to make sure you get osmotic equilibrium. So if you increase the osmolarity of the extracellular fluid, where is water going to want to go? If I increase the osmolarity of the extracellular, it's going to want to leave the cell to the point where then they're balanced. Not necessarily the osmolarity will be normal, but it will be balanced. If you decrease the osmolarity of the extracellular fluid, water is going to want to go into the cell to the point where then we've reached equilibrium. Okay? So the thing is, you have to figure out, what did I do to the extracellular fluid? Did I change the osmolarity, or didn't I? And if I did, what direction is the fluid going to move? And you got to figure out what happens to the osmolarity if I do change it. What happens to the volumes? ICF, ECF. Those are going to be, we're going to give you 6 clinical scenarios to go through. Now these pictures, those you have the book, they bought my book, they messed up a couple of the images, okay? So I'm just warning you. So here's the way we're going to depict what's going on. You can just use word form, or if you're a picture person, you can use the picture. My box, that box represents the normal box represents the fluid that's in your body, ECF and ICF. And I've subdivided. In the blue would represent the fluid in the ICF, and we're going to use the x-axis to represent the amount in liters. Green represents the extracellular fluid volume. The y-axis represents the osmolarity. If you see the thing go up above that black line, there means there's been an increase in osmolarity. If you see it go below the black line, it says there's a decrease in osmolarity. If you don't like pictures, just look at the words. I wrote it down. Now notice this terminology. This terminology applies to what has gone on with the extracellular fluid. Contraction means there's less fluid in the extracellular space or compartment. Expansion means there's more. If you see isoosmotic, hypoosmotic, or hyperosmotic, that tells you what has happened to the osmolarity. Isoosmotic, it has not changed. Hyperosmotic, it means it's gone up. Hypo, it means has gone down. And so what you're seeing is the tail end. What happened? I did this. Water did its thing. This is the final snapshot. Okay? So I've given you 6 clinical scenarios, the 2 easiest ones. Okay, the first one I have, to remind me so I don't have to keep flipping back and forth, is I infuse someone with isotonic saline. Isn't that one of the scenarios? Put a little IV bag in you, give you isotonic saline, 0.9% saline, right? Say yeah, is it one of the scenarios I've listed for you? Okay, just making sure. Now, if I infuse you with isotonic saline, it's going to go into your blood and your extracellular fluid. Have I changed your osmolarity? No. Okay. But have I changed the volume? Yes. And so which of these would represent what you would get if I infuse you with isotonic saline? You would have isoosmotic volume expansion. Okay? What do you, I mean, very shortly, though, after they do that, if I give you that and you're not dehydrated, aren't you going to pee it out at some point? And then eventually you're going to be okay? This is an example. If I just infuse you with an isotonic fluid, all you're going to do is change the volume of the extracellular fluid space. That one's an easy one. Which of those 6 scenarios would represent isoosmotic volume contraction? So we have not changed the osmolarity of the extracellular fluid, but you've lost fluid from the extracellular space. Which one of them do you think it would be? So you somehow would be losing isoosmotic fluids. You're losing fluid and solutes at the same time. Nope, not sweating at the desert. Diarrhea. When you have diarrhea, you're losing fluid and the contents in it. That is isoosmotic volume contraction. Another example would be hemorrhaging. You're losing fluid and electrolytes. So let's do the sweating in the desert, since Dallas mentioned that. So when you sweat, I know what you're thinking. You're losing salt and water, but you lose more water than you do salt. Especially if someone's been acclimatized to it, you're going to lose a lot more fluids than necessarily salt. So if you lose a lot more fluids than salt, all right, so let's figure this out. I'm sweating in the desert. I'm losing a lot more fluids than salt. What is happening to the osmolarity of your extracellular fluid? It's increasing. You're losing the fluid, but not all the salt. So your osmolarity of the ECF is going up. So the way you can start, I always draw myself little pictures. So I make a little cell, and I'm like, okay, where's the osmolarity greater? And I put a lot of dots to indicate the salts. So this is the ICF. This is the ECF. And you said, okay, in the extracellular fluid, I'm losing a lot of fluid but not as much salts. So who's going to be more concentrated, ICF or the ECF? Which one? ICF. Okay, so I'm like, oh, where does water want to go then? Where does water going to want to go? It's going to want to go into the cell to the point where the osmolarities are going to be the same, not going to be normal, but they will be the same. So what will happen to the volume of the intercellular fluid compartment as water enters it? It will increase, okay? So ICF volume increases. So we got a couple of them that says ICF volume increases. What happened to the ECF? We were sweating. You were losing fluid. What happened to the ECF volume? it went down. And what do you say, what set the ball in motion? What happened to the osmolarity of the ECF when you lost that fluid but the salts were still there? It increased. So we're going to call this one hyperosmotic volume what? Contraction, because you've lost fluid in the extracellular space. So this one would be where we got hyperosmotic volume. Where are we? Middle top? Yes. But no. No. Something's not right.
Because it says ICF and ECF decrease, it should say.
Oh, yeah. Because it should be ICF's going up, ECF is going down. It should be high. Something's not right here. It's driving me nuts. Might be the picture. But it should be hyperosmotic volume contraction. Oh, hypo. That's it. Sorry. Thank you, Jenny. Hypo. I'm brain dead, too. This one. It was right. I would just... Okay. It is hypo. She was like, thank you, Jenny. It's like, she said, hypo? I'm like, yes. Okay, so it's hypo. Sorry. Affected by... Just, you guys are rubbing off on me. All right. Okay. Here we go. All right. So this one is sweating in the desert. Okay? Sweating in the desert. Wait, no, it's still hyper. No, it is hyper. Yeah, it's hyper because you get loss of fluids and you get more concentrated. It is hyper. That's why the water went to the cell. Oh, it. Let's step back. I'm going to draw myself pictures. This is better. Here, let's. I'm going to draw a picture. It's easier for me. Here, I'm going to draw a picture, and we'll do it. Those pictures probably should be right. The ones in the book aren't. All right, so here we go. Actually, what we can do is let's skip the sweating in the desert right now. Let's just skip that one for now. Yeah, and then we'll come back to that one. All right, let's ingest salt. Let's do that one. Ingest some salt. Take a salt shaker and eat the salt. Okay? If you do that, what happens to the ECF osmolarity? Eating a whole bunch of salt. It's going to increase. So automatically, I'm going to say hyperosmotic, so before I screw up. Okay? So, where does water want to go? Inside, or it wants to go out? Okay? So ICF volume is going to decrease. What's going to happen to the ECF volume? It's going to increase because it's getting it from the ICF. So ECF volume increases, ICF decreases. What are we going to call this one? We're going to call this hyperosmotic volume expansion. And the way to remember this is I say, what's the effect of people consuming a lot of salt on their blood pressure? Tends to increase their blood pressure because of the volume expansion that results. Okay? So that's a way to try to remember it. So eating a whole bunch of salt could lead to hyperosmotic volume expansion. Okay? So we got the isoosmotics out of the way. We got one of the hyperosmotic. What's the other one? What's our next one? Give me the other scenario. Adrenal insufficiency. Okay. Adrenal insufficiency, we're talking Addison's disease. Okay? Biggest one they were talking about, loss of aldosterone. Little aldosterone loss. What does aldosterone do? Causes you to retain what? Sodium. But I've lost the aldosterone. So what? You're going to lose a lot of sodium. Okay? You're going to lose some sodium. So what happens to the osmolarity of the extracellular fluid if I don't have aldosterone around? It's going to decrease, so I'm going to put all my dots inside the cell because I'm doing a comparative. So I'm going to have a loss of solutes from the extracellular fluid. So it's going to be hypoosmotic. Where does water want to go? Inside the cell. ICF volume is going to increase. What's going to happen to the ECF? Decrease. So hypoosmotic volume contraction. Remember, people with Addison's disease, usually the reason why they first appear, they're in their emergency room because they're in shock because of the loss in blood volume and their blood pressure. So they have hypoosmotic volume contraction. What's the next one? It's abbreviated SIADH. Is that what I had in there? Okay, syndrome of inappropriate ADH secretion. So they actually secrete a lot of antidiuretic hormone, a lot of it. What does antidiuretic hormone do? I introduced it to you like one of the first lectures. Yeah, it allows us to, like in the kidneys, keep our urine in, or fluids in. You want to get the bad stuff out. So it changes the permeability of nephron tubules to water. If you oversecrete ADH, you're going to hold on to a lot of water, and it can lead to what we call water intoxication. Okay? So I'm holding on to a bunch of water. I haven't changed the solutes, but I'm going to change the concentration. So I have all this water. What happens to the osmolarity of the extracellular fluid? All this extra water now. It's going down. So here, the concentration of the solutes inside the cell is greater. Water is going to do what? Want to enter the cell. So ICF volume is up, but we have hypoosmotic volume expansion. Why? Why is it expansion? Because the whole thing that set it off is all the extra water that we had in the extracellular place because the ADH is you're over-secreting ADH. So you have hypoosmotic volume expansion if you over-secrete antidiuretic hormone. Okay? Make sense?
And that's the same as drinking distilled water, correct? That would be the same outcome.
If you drank a whole bunch of distilled water, yeah, it would be the same. Yeah, that would be another scenario. If someone drank, or I injected you with a bunch of distilled water, that would be a similar scenario. Okay, that would be another example. All right, so we've got our hypoosmotics. We have the hyperosmotic. So the one of being sweating in the desert should be hyperosmotic volume contraction. Okay, so let's go through it again, make sure Dr. Case doesn't screw up. Okay, so I said we sweat in the desert. We're losing fluids because we're sweating, trying to cool yourself off. So the outside of the cell gets more concentrated because you're leaving the electrolytes there. So this is hyperosmotic. And why is it volume contraction? Because you lost the fluid because you're sweating. What happened to the volume in the ICF? It decreased. There you go. Let's do one more scenario. This is hyperosmotic because you lost the fluid. You lost the fluid and the salts are staying there, so it's hyperosmotic. All right, let's do one more. We're Talked about inappropriate ADH secretion, hypersecretion of ADH. What if I have diabetes? What?
You said ECF increases. That's what's wrong with that.
No, ECF decreases because you've lost fluids because you're sweating in the desert. It's contraction. You have a little bit of fluid leaving the cells, but not enough to make up for all the loss that you were sweating out. So it's volume contraction. ICF decreases. All right, if you're in the book, definitely the pictures are messed up. Okay. All right, what about if I have diabetes insipidus? What's diabetes insipidus? Well, that could be nephrogenic diabetes insipidus, is my ADH receptors aren't working, or if I have neurogenic, I'm not making ADH. Okay, so if I don't make ADH, what happens? What's the problem? I'm peeing a lot. All the time. Oh, yeah, all the time. So you pee all the time, and you're going to lose a lot more fluid than you do electrolytes. So you're just going to lose a lot of fluid because ADH does not affect solutes, it only affects water. So if I pee all the time, what's going to happen to my extracellular fluid volume? My ECF volume is going to do what? It's going to decrease. What's going to happen to the osmolarity of the extracellular fluid? It's going to increase, okay? Because I'm just losing more water. So we have, this would be hyperosmotic volume contraction. What's happening to the ICF? It's going to go down. Okay? So there's more than one thing that can cause these different scenarios. So if I don't make ADH, it's a hyperosmotic volume contraction because I'm losing all that fluid with a lack of ADH. Could that be bad? Can any of these be bad? Because if you change cell volume, you're going to change how that cell functions. Just think about any of these. These cells could be any cell in my body. What if it's a brain cell? If you have a brain cell that shrinks or expands, can that affect how it's firing and then how it's communicating there? Yeah. So you can cause a lot of problems. Okay? If it swells and causes seizures, contracting and going being unconscious, so affects the brain, it's going to affect a lot of things. So those are just a couple scenarios for us. So let's see if I can think of some other scenarios. I'll do it, but not right now. Just go by the words. Go by the words. So let's make a table so you can get it. So we'll just make a table real quick. So someone tell me real quick. We said infusion of saline. So ICF volume, what did it do for infusion of isotonic saline? No change. ECF went up. Osmolarity, no change. We had diarrhea. ICF, no change. ECF, down. Osmolarity, no change. Then we had adrenal insufficiency, lack of aldosterone. Okay, so that one, what do we put? Osmolarity did what? Lack of aldosterone, you can't hold on to sodium. It went down. Okay, so I'm going to do my little picture again. So it went down. So what happened to the ICF? volume? It goes up. What happened to ECF volume? It went down. Then we've got, what was the other one? SiADH. So osmolarity. And then you're holding on a bunch of water. So the osmolarity is going to go, it's going to dilute everything. Goes down, okay? You're over-secreting ADH. So the osmolarity went down. What happened to ECF volume? Because remember, you're holding on a bunch of water, it's up. And then ICF volume did what? Went up. Then were they sweating in the desert? Osmolarity increases, ECF down, ICF down. And our last one, what was the last one? Oh, yeah. Eat a lot of salt. Osmolarity went up. ECF is going to go up, and ICF is going to go what? Down. Okay? Your ECF was going to go up too with that eating a lot of salt, because guess what it does? When your osmolarity goes up, guess what happens to ADH secretion? It's going to go up. So you're going to hold on to some more water to try to balance it up. So it makes it even worse. All right, so there's just a table form. Okay? So you either put isoosmotic here, hypoosmotic, hyperosmotic, and then depending on what goes on with the ECF, say expansion or contraction. Okay? All right. Bless you. All right, last topic. Usually I don't even cover this anymore because we did it last trimester. Didn't we cover edema last trimester? Talking about changing the forces. So I'm not going to talk about it. And you're like, oh, do you remember that, Gordon? Like, it's like, oh, I kind of remember that equation in a little way. I'm going to cover it again. Guess what? When we do some of the stuff regarding the kidneys, I'm going to talk about these forces. Okay, why do we have this much filtration in the glomerulus? It's going to come down to talking about pressures again. So I'll reserve that for later. Okay, so don't worry. So I told you I'll let you out a little early. I usually somehow cover that a little bit later. Okay, so I'll end it early for you guys. Okay, or we can keep going.